session of today. And we are happy to have Chris White, and he will tell us about the classical double copies, the view from twistor space.
Great. Well, thanks for the invitation, and also thanks for this wonderful idea of organising a virtual conference. I'm sure some ideas like this will stay in the future. But yes, what I thought I'd do for my talk is combine something that's quite close to my heart, which is the classical double copy, with something that lots of other people at the conference might care about, which is twistor theory. Right, let's change the slide. Okay, so yes, this is basically going to be a talk about the classical double copy. So that it doesn't need much introduction for this audience, of course, but that relates solutions in gauge and gravity theories, also related theories like biadjoint theory and so on. Now that, of course, is closely related to the original double copy for scattering amplitudes. It's kind of like an off-shell generalization of it, if you want to think of it that way. And there are many different approaches now to classical double copies on the market. So apologies for the lack of names here, but there would be many. And in most of those approaches, you're confined to really working with classical solutions only order by order in perturbation theory. Now that's not necessarily a problem because for gravitational waves or something, that's what one would be doing anyway. It's a very messy system. But there are some cases where you can really make exact statements about the classical double copy, really relate exact solutions. And those are the ones I want to focus on in this talk, because I want to try and figure out where they come from and how much we can say about where they come from. So the first one of these that was on the market, I guess, was the Kkershill double copy. What we did there is, well, first of all, I'll talk about gravitons being defined around Minkowski space, where that's the full metric, and that's the Minkowski one there. And there's a special class of gravitons called Kkershill gravitons, which have a very special form, where the graviton itself is some sort of outer product of a scalar field and an outer product of a vector with itself. That vector has to be null, and it has to be geodesic. And it turns out that those solutions have very nice properties and you can solve for them. Now, the point is about those gravitons is they have such a nice form, it's quite clear how to take their single copy. So to go to a gauge theory, one just strips off a K vector, replaces it with a constant color vector, and one can show that gauge field satisfies the linearized Yang-Mills equations, so where they exactly linearize. And likewise, if you repeat the procedure, you get a biadjoint scalar field. Now, when I say those linearize the respective field equations, there are no nonlinear corrections. So what you get is really an exact set of solutions that are related by the double copy exactly analogously to how amplitudes are related in the biadjoint, gauge, and gravity theories. So it's really very analogous. And as the years have gone on, we've understood quite more how they're related. Now, there is also a second exact double copy relationship that has been presented, a very nice one called the Vial double copy by these authors that I'm listing here. Now, I cannot just state that because it relies on a formalism for GR, the spinorial formalism, which is textbook stuff, but not everybody knows it. So I thought I would give some brief introduction to it. So yes, it's a formalism in which all the field equations are written in terms of two-component spinors. So pi here is a two-component Vial spinor, and A is an index that goes from 0 to 1. And we normally denote the complex conjugates of these spinors by putting a primes on the indices. So this pi A prime there. Now, if you haven't seen this before, rest assured that if I give you any tensor with space-time indices, you can contract it with things called Infeld-von der Waals symbols, and that will convert you into the spinorial language. So each space-time index ends up as a pair of spinorial indices in the two-spinor language. And just to show you that these things are just matrices of constant numbers, if you've not seen them before, you have to choose a suitable basis. But once you do, then these things can just be worked out, and then you can convert between the two languages very easily. Now, of course, once you have spinor indices, you probably might want to raise and lower them. It turns out that you do that with the two-dimensional Levi-Civita symbols. Now, what is the use of this language? Well, it actually makes many structures in general relativity and other theories particularly clear. So it turns out that all spinors with multiple indices can be reduced to sums of products of Levi-Civita symbols and fully symmetric spinors. So that's already some structure that emerges. You only really have to worry about fully symmetrized spinors, by which I mean you can do a symmetrization over all the indices and get the same thing. So for example, the electromagnetic field strength tensor translates as follows. It will have two spacetime indices that will turn into 4 spinor indices. And indeed, we see that it has this phi AB, which is a symmetric spinor, times a Levi-Civita symbol. And likewise, there's another part here where that's the conjugate of that. And these are called the anti-self dual and self-dual parts, because if you work out what the anti-self dual and self-dual parts of the field strength tensor are, they are those phi and phi bars that I've written down. Now in gravity, you can do a similar thing. I'll be concerned with vacuum spacetimes, and then the Riemann tensor reduces to something called the Vial tensor, and that has the following spinorial translation. So again, we have a self-dual and an anti-self-dual part. That now has 4 indices in each of those, because we have 8 indices in total with the Levi-Civita symbols, which is what you get from the spinorial translation. So you can then ask, what are the field equations in this language? And the vacuum, Maxwell and Einstein equations have a nice simple form, and in fact a very related form, because they turn out to be special cases of what's called the massless free field equation. So I've written them here. There's one for the phi quantity, one for the phi bar. The nabla thing here is the spinorial translation of the covariant derivative. But anyway, those are the 2 field equations that you get. And you have 2 n indices for a spin n field. That follows directly from these spinorial translation rules. But indeed, above you see the electromagnetic solution has 2 indices, spin 1. The gravity one has 4 in the Vial spinner. So far, so good. Something else that emerges nicely in this language is that all fully symmetric spinners can actually be decomposed further. So there's this great, wonderful structure that emerges when you use this language. And you can write any symmetric spinner, it turns out, as a symmetrized product of spinners with only 1 index. And those are called principal spinners for the obvious reason that they somehow reflect these kind of the main bits, if you like, of the spinner that you're decomposing. So the electromagnetic and the Vial spinners can be written as follows. The electromagnetic spinner can be written as a symmetrized product of 2 things, and the Vial spinner is a symmetrized product of 4 things. Now, why is that nice? Well, one of the things it's useful for is it allows you to classify different solutions. So there are qualitatively different types of solution depending on the pattern of the principal spinners. If I take the electromagnetic case, those spinners could be proportional to each other, so they're really kind of like the same thing, or they could be different. And we call those null or non-null, respectively. For the Vial spinner, there's clearly a lot more cases that you have to consider, but really it's just a statement about the pattern of degeneracy of the principal spinners. So they could be all different, which is what this curly bracket 1111 is meant to mean. They could be 2 of them the same and 2 distinct, and so on. And for nice historical reasons, those are called Petrov types, and this is called the Petrov classification. So in the tensorial language, you can also write down the Petrov classification. It's much more cumbersome. In the spinorial language, it becomes a very nice, simple statement about the patterns of the principal spinners of your Vial spinner. Now, I should say, for those that haven't seen this before, Petrov type D is not a unique solution. There are lots of solutions of Petrov type D, for example, but it's just a nice way of classifying solutions into different types. I can now state the Vial double copy and hopefully do as good a job as the authors did in their very readable paper. But what they said is that if you take 2 electromagnetic spinners, you can generate a Vial spinner according to the following rule. So generally they take those electromagnetic spinners to be the same, but they don't have to be the same. So I can put a tilde on one of them, and that just means it could be different. And then you just multiply them together, symmetrize over the indices, and then divide by a scalar field that turns out to satisfy the linearized biadjoint field equation. So this does rather look like the other classical double copy approaches, in that you have a product of electromagnetic solutions to make a gravity solution. You divide by the scalar, because if, for example, you were using the Kkershill approach, that would be sitting in the electromagnetic solution. So you've kind of included it twice and you have to divide by it. So this was a very nice result. And it's known, I think, to be more general than just the Kkershill double copy. So when we talk about exact classical double copies, I think this is kind of the cutting edge of them. What are the other details of this? So it's not necessarily known, I think, in that paper, how to fix this scalar function a priori. But if you have examples of given gravity solutions and electromagnetic ones, you can just equate both sides and match them and read off what this thing has to be. And the authors, I say here, they argued, they showed, I believe, so I should have written it more strongly than that, I apologize, but they showed that this holds for general vacuum type D spacetimes, and that it's entirely equivalent to the Kkershill double copy where they overlap. So there are cases of the Vial double copy that are not known to have necessarily a Kkershill counterpart, but it's where they do overlap, it's actually fairly straightforward to convert between the two pictures. Now, when I first looked at this Vial double copy, my first thought was, well, where does this actually come from? This has a very particular form. Clearly, the symmetrization here is because we need something symmetric on the left-hand side, but it would be nice if there were a little bit more justification about whether we could derive this form from some kind of more underlying principle. And I think also there's a lot more open questions about these exact classical double copies. And those open questions are worth looking at, because if we don't even understand the exact cases, how can we know how general the full double copy is? So these are some open questions that have puzzled me over the years. First of all, why is it possible to formulate a classical double copy in position space? Because the BCJ procedure normally involves products in momentum space. And indeed, the double copy that Sylvia Nige was talking about this morning has a convolution in position space, which is what you'd expect for a product in momentum space. So it's always been a bit of a puzzle why this thing works in position space. So we'd like to explain that. Also, we have the scalar function in the Vial double copy, and it would be nice to know how to fix that and where it kind of comes from. Something that has puzzled me for years, really, is how do we formulate the inverse zeroth copy? So we know if we have a gauge field, it has something in it like a biadjoint field times a 4 vector, and we can strip the 4 vector off and we get just the biadjoint field. If I just gave you a scalar field and told you, make a gauge field out of it, I don't think it would be very clear what you actually had to do. It seems ambiguous or just not even known how you dress the scalar field to make a gauge field and a graviton. So giving an operational meaning to that inverse zeroth copy is something that would be very nice to do. The other thing is whether the exact classical double copy can be formulated in curved backgrounds. So I talked about gravitons earlier as just being around Minkowski space, and the type 2 vacuum solutions are like that because they have this double Kkershill form that is really just around Minkowski space. But there is some preliminary evidence that we can actually define the graviton around a curved background, particularly a conformally flat background, for example, and that should work. Now, it's not fully known whether that should work, but there are hints, so it'd be nice to explore that. And then finally, it would be nice to see if this Vial double copy is more general than type D. If we really want to explain the origin of the double copy or classify where it works, where it doesn't, we'd like to know, can you do less algebraically special cases? Now, there is a reason why I have written this list of open questions, because I think I can answer all of them, or at least give some sort of answer to all of them. And I'm going to do that by going to twistor space. So I said just now, not everyone will be familiar with spinners, or at least with the spinner language for GR. Certainly then not everyone is going to be familiar with twistors. I cannot possibly teach you twistor theory in sort of 2 minutes. You probably want to read books like this. But I will at least try and give you some small facts that I will use to derive the Vial double copy. So yes, let me start by saying that twistor space T is the set of solutions of what's called the twistor equation. So that just is some equation where you have a spinor field with one index, and then this is the spinorial translation of the covariant derivative that's acting on it, and there's a symmetrization there over the indices. And the general solution of that can be written down quite straightforwardly in Minkowski space. Omega and pi here are constant spinors, and x is the spinorial translation of a space-time point x, and that arises because we have a covariant derivative on the left-hand side. Now that means then that solutions of the twistor equation can be associated with pairs of these spinors. So I can put this spin omega and pi together, I can bolt them together, put brackets around them, and call that something, and call it a twistor, in fact. So alpha here is an index. Confusingly, it's not an index here in space-time, it's an index in twistor space. It is labeling which component of that 4-component object I've made I'm talking about. So there are 2 components in one of these spinors, 2 in the other, so it's an index that goes from 0 to 3. Once we have twistors, so a point, if you like, in twistor space is just one of these twistors. Its location in space-time is just defined by the vanishing of this field omega A, and that leads to something called the incidence relation, namely that this omega A and this pi A prime are not independent, but they're related by this relation. Now, if we look then, that relation has caused us to make a map between space-time and twistor space, because it satisfies, or it indicates there's some relation between the twistor variables and the space-time variables. Now, the other thing we notice about that incidence relation is that it clearly doesn't care if we rescale the twistor, because that rescaling will cancel out on both sides. So twistors obeying the incidence relation are not points in twistor space, they are points in projective twistor space, where projective, as usual, just means that we've modded out any possible rescalings. The next thing I want to tell you is that what are the details of that map? So if I have a fixed point x in Minkowski space, what does it map to in projective twistor space? It turns out to be a Riemann sphere, or a complex line is another way of thinking about it. And that sphere turns out to correspond to the set of all possible null directions at the space-time point x. Now, that is not necessarily obvious if you've not seen this before, but it does follow from everything I'm saying. And we'll use that fact a little bit later. Finally, if I have twistors, I can take their conjugates to make things called dual twistors. I do that by taking the complex conjugate of this equation, so we can give a meaning to lowering the index. And then we can make inner products, and those turn out to be conformally invariant. So that, for the uninitiated, is why twistors are so ubiquitous in modern amplitudes research. They make conformal invariance manifest. They're the right variables to use. So the next thing in our course on twistor theory is something called the Penrose transform. It turns out that if you have functions in projective twistor space, those turn out to be related to space-time fields. So in other words, to solutions of the massless free field equation that I showed you earlier. Now, a mathematician would have a go at me at this point. I really mean cohomology classes, not functions, but let's be rough about this. If I take some functions in twistor space, so I really mean here by a holomorphic function in the slide, I mean a function that has no non-constant dual twistors. But if I take such a function and I restrict it to obey the incidence relation at a certain space-time point x, I clearly get something then that has to depend upon that space-time point x on the left-hand side. I can then make a contour integral where that contour exists on the celestial sphere of x, so on this Riemann sphere corresponding to the point x. The integral has some pi's in it. Remember, those are the spinors that are sitting inside the twistor. But by doing that, I introduce some free indices on the right-hand side that have to be there on the left. And then finally, I can just integrate over this whole thing, and I get something that should have a number of free indices and depend on the space point x. So that much is obvious by looking at the right-hand side. What's not obvious is that indeed obeys the massless free field equation. So this is a kind of classic result of twistor theory. Now, what can we say about what these functions have to look like? Well, first of all, they're functions in projective twistor space. The whole point of that is that I'm not supposed to be able to notice whether I've done any rescalings. So the whole integrand, including the measure, has to have homogeneity 0 under rescalings of the twistor. And that means then that if I want n indices on the left-hand side, this function has to have homogeneity -n-2. So I'll use that fact in a moment. And finally, I will point out a slight caveat to what I was saying above. For scalar fields, you can't really write down the massless free field equation, but you can consider the right-hand side of this formula. And indeed, that scalar field turns out to obey the conformally invariant free field equation. So it's not just the linearized biadjoint equation. It actually has this conformal coupling to the Ricci scalar of the background that you're talking about. So yes, that's a lot of information, but I've now told you enough to derive the Vial double copy. So let's do so. What I want to do is consider, first of all, two functions in twistor space with homogeneity -4. Now, those necessarily, by the Penrose transform, will correspond to electromagnetic fields in position space. Then I could also consider a function of homogeneity -2, and that will necessarily correspond to a scalar in position space. And by the rules of maths, if I multiply them together in this combination here, I get a homogeneity -6 function. That necessarily has to correspond to a gravity solution. So merely the known facts of twistor theory tell me that there is some sort of space-time relationship between electromagnetic fields and scalars that has this form. Now, my claim then is that at least for certain choices of these functions, and I merely have to find them, the corresponding space-time fields from the Penrose transform obey exactly this relationship I've written down here, and that is precisely the Vial double copy. So if you like, the twistor space picture here has given us a derivation of the form of the Vial double copy, which is what I wanted to set out to do. Of course, the Vial double copy was known to work for type D solutions. All I have to do to convince you of that is show you a family of functions that does the job. So if I plug it into that product in twistor space, I get the type D Vial double copy. Now, I can tell you in more details why I was led to this class of functions. But I'm going to take a general quadratic form in twistor space, raise it to a negative power, where the homogeneity scaling of that function is different for different powers. So n there has to be 1, 2, or 3 for scalar, electromagnetic, or gravity solution. That is a combinatorial factor, the m factorial, that is not really important to talk about. And it turns out, indeed, that if you plug that in, you get the type D Vial double copy. How would you show that? Well, I can do the Penrose transform of these functions by going into some coordinates in twistor space. Because it's invariant under rescalings, I can choose the first component of this pi spinor to be 1, and then the other is just some arbitrary complex number. If you do that, this function will turn out to have this general form. So it will have some poles on this Riemann sphere corresponding to the space-time point x. It will have some normalization factor, which I've chosen to write like this. And the space-time dependence there is coming from the incidence relation that has to be applied in that Penrose transform. And if you carry out then the Penrose transform, you get these results here, where alpha and beta are some spinors that are completely determined by the poles of this function in twistor space. Now, you can look at these fields. They clearly obey the type D Vial double copy. That gravity solution is a type D solution, and so on. Now, the other thing to note then is that these principal spinors are completely fixed by the poles of the twistor space function. So it gives us a new way of thinking about where those principal spinors come from. That's a very abstract discussion. So let me give a specific example. The easiest example you might want to do, because it's what everyone who does a classical double copy starts with, is the Schwarzschild solution. Because we're just talking about the self-dual part of the solution, the Vial spinor, then really it's some sort of Taub nut mixed with Schwarzschild to make a self-dual thing. But anyway, this is the relevant quadratic form to use in this case. This is the Q matrix that you have to use. These are some poles in twistor space. They're just functions of the coordinates in space-time. And then this is the normalization factor. So that's not so important for us to worry about now. I have made a point of showing what the scalar function is that you get when you work this through. R there is the usual spherical radius in space-time, but that is exactly the function that was found by matching in the original Vial double copy paper. So it's nice to see those results coming out indeed as a cross-check of this formalism. If you wanted, so if you don't know about the Vial double copy, but you do know about the Kkershill one, how would you convert between the two? You can take the principal spinors that come out of this, you can contract them with the Infeld von der Waerder symbols that I showed you earlier on, and you get the null vectors K mu that you need for the Kkershill's double copy. And indeed, I've done that calculation, and you get two possible choices, which are the two choices that you would use. Now, an obvious question then is, well, fine, you've showed a specific case. Do you get all type D vacuum spacetimes out, what are called the Plebanski-Demiansky solutions that were considered by the original Vial double copy authors? The answer is yes. Different choices of Q indeed map out that space of solutions. As justification, I will cite an old note by Linda Hazelhurst and Roger Penrose in Twistor Newsletter. And for those that are unfamiliar with the wonderful periodical that is Twistor Newsletter, the likes of which will never be seen again, it is archived on Lionel Mason's website. So, many thanks for him for doing that valuable service to the community. But anyway, there are also general arguments one can give, so you can ask me about those at the end. Right, yes, so what is this good for? I hope I've convinced you that the twistor space picture explains where the Vial double copy comes from and why it exists in position space. The Penrose transform relates twistor functions to position space-time fields, and that's why it works. So the scalar function that appears is no longer mysterious, but fixed. You choose your functions accordingly, and you know what the scalar will be. The thing that I really like about this, just because I puzzled a long time about this inverse zeroth copy, is that this does give a nice meaning, I think, to the inverse zeroth copy. We saw that the extra kinematic information that is sitting in the gauge and gravity fields, what is that extra kinematic information? Well, it's those principal spinors that are not there in the scalar solution, but are there in the gauge and gravity solution. Those principal spinors were entirely fixed by the poles of the functions in twistor space. Those poles are already there in the scalar function. So there is a very well-defined sense in which the scalar knows already about the principal spinors that are going to be in the gauge and the gravity solution. So that gives an operational meaning to the inverse zeroth copy, I think, for the first time. And that's something I think that's very nice, and perhaps needs to be thought about a little bit more, actually. The other thing I should say is that in principle, of course, the twistor language is conformally invariant, and that means that the Vial double copy should immediately extend to conformally flat spacetimes, generalizing previous results. I could really say they're formalizing previous results. It makes specific what you have to do, I think, to get a full conformally flat analog of the classical double copy. You could do it, knowing the twistor facts, you can actually do it just in spacetime, I think, by just taking your set of fields that you get in spacetime and conformally transforming them according to the usual rules of conformally transforming spinors. There's somewhere in this 1,000 pages of Penrose and Rindler, and you'll get a set of fields that obey the curved space double copy. So it'd be nice to construct explicit examples of that. The last thing I want to say is that you can do more general Petrov types with this. So there is a nice Penrose transform pair that appears in some condensed matter papers for interesting reasons, which I can go into. This is what's called an elementary state on the left-hand side in twistor theory, and it has some form in position space where A and B here are some constant spinors. And if you make different choices for these integers A and B, you get a scalar field two different choices of electromagnetic spinners, and you can multiply them in different ways according to the twistor rules I gave you. And one of them is a solution of type 3. So the Vial double copy is indeed more general than previously thought. The price you might pay, though, by going beyond type D is because the Penrose transform is only actually limited to linear field solutions. They might give you solutions at linear level only and not with nonlinear corrections. However, there are nonlinear generalizations of the Penrose transform, so this could be thought about and generalized a bit more. I've probably gone on long enough, so let me conclude. The Vial double copy is an exact relationship between classical solutions in biadjoint gauge and gravity theories. Twistor theory, I think, resolves a number of open puzzles, where the Vial double copy comes from and why it works in position space, how to fix that scalar function that appears in it, how the gauge field inherits information from the scalar theory, what's called the inverse zeroth copy, why the double copy should also work in general conformally flat spacetimes, and why it should also work for less algebraically special cases, i.e. not just Petrov type D. Now, there is clearly much more that can be done. I mean, I've barely scratched the surface, I think, of what can be done with twistor theory here. There are certainly people at this conference that know a lot more twistor theory than I do, help develop some of it. So I'm sure that there are many things that can be done. I'm certainly up for having discussions if people want to know more or discuss things. And I've created a discussion channel following the instructions from JJ, which I've called Vial from Twistor Space. So I'll post that in the coffee as well, a chat box thing. So yes, thanks for listening.
Thank you very much for a nice talk. Well, we are out of time, so let's take urgent questions. So Lance has an urgent question.
Hey, Chris, thanks for that nice talk. Is it true that every gauge solution in your talk today was a solution to Maxwell and not Yang-Mills?
Yes. And
is it possible to do it with Yang-Mills without ghosts? I think there's ways to do it with ghosts, but I wondered if you thought there were ways to do it without ghosts.
Well, let me first say the reason it's limited to electromagnetic solutions is just that the Penrose transfer that I'm using gives you specifically a linearized solution, so an electromagnetic field. The twistor picture could certainly be extended, I think, to Yang-Mills because there are non-linear generalizations of the Penrose transform that give you Yang-Mills solutions, things like the Ward construction and so on. So yeah, I would have to know a little bit more about those Yang-Mills generalizations of the Penrose transform to fully answer your question, I think.
Okay, I also noticed you had a paper from August that talks about self-dual Yang-Mills and Blavatsky, and that seems to be in the direction I'm interested in, but maybe you're thinking of that in a different way, since you didn't mention it.
Yes, I thought in a short talk like this, I'd concentrate on the one idea that's in this.
I mean, is that a legitimate double copy with a legitimate non-abelian solution in it, or would you characterize it differently?
Well, that paper looks at the self-dual sector, where indeed the double copy is very well understood. Now, in fact, it's precisely the self-dual sector where a twistor language should be known.
Okay.
So it actually it does relate to what I'm saying in this talk.
Yeah.
Now, as to where the ghosts come in, I mean, for these, well, of course, the self-dual solutions themselves are already very special. So whether that means this complication doesn't occur, I would just have to think a bit more about this, I think, to be able to answer.
Thanks a lot.
Thank you. Let's go quickly to Alfredo. Quick question.
Hi, Chris. I have 2 questions. I guess I will save one for the Slack. But one question would be, so in the Kerr case, we know that this killing spinner can be obtained from a Newman-Janis shift, even from some sort of the Newman-Janis shift, even in the twistor space, right? So I guess this Q that you define is actually the killing spinner that Newman and Penrose construct in his book. But also, Donald and company have shown that you can get the Tau-NUT solutions, right, from a similar kind of shift. So is this a general construction that you can do in twistor space to this killing spinner?
I would have to know more about what you're talking about, I think, too, but it sounds very interesting to be able to provide an answer to that. Yeah, I mean,
okay.
The answer could be yes, but I just don't know enough.
Okay, yeah, okay, thank you.
Okay, so thanks a lot, Chris, again, for a great talk.